Hi, this is a hopefully not too terribly long, sort of rough guide to handling objects that follow the projectile motion particle model, the PMPM. And kind of the most important thing to understand in this model is that if we're talking about a projectile, then once the motion is started, it's only subject to the downward force of gravity, Fg here. There are no forces acting in the horizontal direction, so for that reason, horizontally, it is CVPM because it's BFPM. There are no forces acting horizontally here. Vertically, you have just this one force acting downward. There's not an upward force to balance that out. So vertically, it is CAPM because it is UBFPM. Okay? So that means that any projectile motion problem is actually two problems. You're going to have one problem for the horizontal velocity, Vx, little subscript x to represent that it's horizontal, and that's going to look something like this. So constant velocity, the change in position horizontally, which is sometimes referred to as the range, is just going to be the area underneath that graph. So range is just purely talking about the change in horizontal position. Vertically, that's a little bit of a different story. Because you have that force acting downward, you're subject to the unbalanced force particle model, and so the vertical velocity, we're going to see constant acceleration. If the object is dropped from rest, then the initial vertical velocity is going to be 0, and it's going to go something like this. Okay, so you have an initial vertical velocity of 0, and that velocity becomes increasingly negative over time. We could have a particle that's thrown with an initial upward vertical velocity, so you're going to start off in the positive part of the graph, and it's just going to trend downward over time, something along those lines. Or it could be thrown at a downward angle, and so there's some negative vertical velocity to start with, and that would go like this. But as best I could, I tried to draw all of these lines parallel because they would all have the same slope, which is commonly referred to as little g, and near the Earth's surface, that's going to be roughly -10 meters per second per second. If you want to be a real stickler, it's something like -9.801 or something meters per second squared. But -10 is good enough for the multiple choice section of the AP exam, so hey, that's good enough for me. Then in looking at the different graph shapes that we might see there in the Vy, for a particle that's thrown upwards and returns to the same height, in other words, it's like a projectile kicked from a level field or something like that, so it's going to have the same original and final y position value, the vertical value. Vy in that case is going to be, let's see here, 1, 2, 3, 4, 2, 3, 4, is going to be kind of nice and symmetrical. 1, 2, 3, 4. There we go. What I'm meaning to say is that this area right here will be positive, and then the area down here below the x-axis will be a negative area. So this represents the up part of the motion, this represents the down part of the motion. If we add those two areas together, the change in vertical position is going to be equal to 0. Okay? A different type of problem we might encounter where if we're shooting a basket or something like that, playing sports ball, the ball doesn't come back down as far as it went up, so its final height is going to be greater than its initial height. Then we're going to see it goes up, but it maybe doesn't come back down quite as far. So the positive area would be greater than the negative area. Or you could have a situation where maybe you throw something at an upward angle off of a cliff, and so the initial vertical velocity positive here. It's going to end up landing somewhere far down below, so it goes up, but then it goes back down farther, so we'd have a greater area in the negative part of the graph. So if we add these two things together, we would see that the initial vertical position is greater than the final vertical position. Okay, so the delta y is going to be some kind of a negative value. Here the delta y would be positive, and here where the graph is symmetrical, that means that the delta y is 0. This is an illustration from the text, and again it's just showing that the horizontal part of the motion, represented by this arrow here, VOX, so the original horizontal velocity, that part of the motion is constant. Okay, so if you can imagine, this is like a motion map but in 2 dimensions. We're always drawing the same arrow length for the horizontal velocity. In the vertical direction though, on the way up to the top, this arrow that represents the vertical velocity is decreasing. Okay, so we would have a downward directed acceleration causing this upward directed velocity to get less and less and less until eventually at some point the vertical velocity becomes 0 momentarily. If we look again at it a little bit later, now we're starting to get an increasingly negative vertical velocity. The acceleration is again directed downward. Now that the velocity is directed downward, we see that the arrow gets longer as the time goes on. So let's look at some applications to some sort of generic problems. Something kind of common would be to say we have a rock thrown horizontally. So what this is saying is that the way the rock is thrown initially, all the velocity is directed parallel to the Earth's surface. It's not thrown at an upward angle, it's not thrown at a downward angle, it's thrown sidearm, so it's kind of going sideways initially. Subject to gravitational force, as soon as it leaves a person's hand, it's going to start accelerating in a downward direction. But at the very beginning, if you see this thing that it's thrown horizontally, that tells you that your vertical velocity starts from 0. So rock thrown horizontally, let's say it lands 20 meters from the base of a 30-meter tall cliff. Okay, because lots of people in physics problems like to throw rocks off of cliffs. So based on this, what could we know? Well, Vx is going to be CVPM, and so it's just going to look like this. And if I find this area, that area is going to have to equal this 20 meters here. That's the distance it moved horizontally. That's how far out it lands from the base of the cliff. The cliff is 30 meters tall. That doesn't show up over here. That's going to show up in the vertical part of the problem. Again, any projectile motion problem is actually 2 problems. So I just kind of draw a rough go at this thing. Where I started, again, this is what is my velocity at time 0. This thing's thrown horizontally, so its vertical velocity at time 0 is going to be 0, and then it's subject to gravitational acceleration after that. And so we're going to go like this, and wherever it ends up at, the only thing I know right now is that this area corresponds to the cliff height. Okay, so it's thrown from the top of the cliff, it lands at the bottom, so this is the change in vertical height, delta y, which is to say yf minus yo, and that's going to be negative 30 meters. Negative, well, the area is below the axis here, and also it's falling, it's dropping, it's going to land below its initial vertical position, so that's why negative 30 here. So that's the area. Now the other important thing that I'm going to know is the slope of this line. Again, we can just use negative 10 meters per second here. Okay, I know the area is negative 30. that's going to be equal to 1/2 base times height. The base over here, that's going to, we can just call that t, and then the height of this thing, whatever t is, this is going to be -10 times that. So if it's 1 second over, we're going to be going -10 meters per second. If we're falling for 2 seconds, then our velocity would be -20 meters per second. If it's 3 over, this is going to be -30 meters per second. That's the pattern for the velocity there. So I'm just going to write -10 meters per second squared t. Okay? And so we work through the math here. -30 equals -5 t squared. -30 over -5 equals t squared. So t squared is going to be equal to, gosh, somebody have a calculator. -30 over -5. Let's see here. 6. So t is going to be the square root of 6 seconds. I can punch that into a calculator here in a second and figure out what's going on. Now, that's the time it's in motion vertically. It's also the time it's in motion horizontally. So now I can come over to my Vx graph, and I know that this is the time here that corresponds to this area, 20 meters, is root 6 seconds. And so I can figure out what is the original horizontal velocity, Vox, okay? Because again, my rectangle will have the area of 20 meters. That's equal to the height times the base of this rectangle, which we just found out was root 6 seconds. Okay, so 20 meters over root 6 seconds, that's going to tell me what the velocity was, or what the speed was that it was thrown at initially. Alright, so root 6, 2.45 seconds. Come back over here with that. 20 meters divided by 2.45 seconds. We're going to get something in the ballpark of 8.16 meters per second. So that would be the initial velocity that this thing was thrown at. So that's one problem type. That's where the thing says something specifically about it being thrown horizontally. The other kind of problem type that we'll have to deal with is a problem where the projectile is launched at an angle. So if we take a projectile and launch it at an angle of, let's say 30 degrees above the horizontal. So I'm going to go find the horizontal, 10, 20, 30 degrees above the horizontal, and let's make it be, for kicks, call that 20 meters per second, 30 degrees above the horizontal. So the trick, if you want to call it that here, is going to be that we're going to have to break the velocity into two parts. Just like in that image we were looking at from the textbook, we're going to have to take this velocity at this angle and decompose it into the original horizontal velocity, which is going to be subject to CVPM, and the original vertical velocity, which is going to be subject to CAPM. So let's see, it looks like it drops to there. Vertical velocities are drawn in red. Let's see what we get here. So this is the upward part of the velocity, and that measures out to be right around, let's see, 5.5. So that's going to be math. This is going to be about 10 meters per second. Okay, and then horizontally, that's a little over 8 centimeters. I made my original arrow 10 centimeters long, so I got to double this here. So it's going to be in the ballpark of 16 meters per second. So now I know to go into my graphs and I have where my CVPM VOX is, and I have where my